All right, ladies and gentlemen, welcome to part 2 of the introduction to atoms, where we're looking at kind of the history of how we've gotten to the point of what we know about atoms now. And so in our last lesson, we took a look at we went back to before the time of Christ with Democritus and his idea that, hey, just maybe everything in our universe is actually made up of smaller things that we can't see, and he called these atoms. Then we fast forwarded about 2,000 years to the time of John Dalton, and we learned about John Dalton's theory that had 4 postulates, where the first postulate talked about the fact that all elements are made up of indivisible atoms, atoms that can't be divided into smaller parts. His second postulate was that atoms of the same element are exactly alike, and that they are different from the atoms of other elements. So oxygen atoms are all exactly alike, but they're different from nitrogen atoms and every other atom. His third postulate was that atoms combine in whole number ratios because they can't divide, so they have to be in whole numbers. And then his fourth postulate and final postulate was that when a chemical reaction happens, the atoms do not change to a different element. They may rearrange and combine with other atoms in different ways, but they don't, you're not going to have an oxygen atom changing into a hydrogen atom. All right. So today we're going to take a look at another gentleman. His name is J.J. Thomson. He lived around shortly after Dalton. He was born about a decade later, and did his work in the late 1800s, early 1900s, and he is famous for an experiment that he did. We call it the cathode ray tube experiment. And in this experiment, he had a glass tube. Inside was an inert gas, meaning one that doesn't react with other things. And then there were 2 metal plates in there. One had a positive charge, the other had a negative charge. And he noticed that when he passed electricity through this, that the particles in the gas were attracted to the positive plate. Well, if they're attracted to the positive plate, his conclusion, they must be negative. Why? Well, because opposites attract. All right, just like the north pole of a magnet and the south pole of a magnet attract each other, and yet the south pole and the south pole repel each other. So his conclusion, if they're attracted to the positive, they must be negative. All right, so we are not going to watch that video right now, but I will have that available for you to watch it on your own. Next, we're going to talk about what it was that he thinks he discovered. J.J. Thomson discovered what we now know as the electron, negatively charged part of an atom. And so after concluding that there were these negative charges in an atom, he decided he needed to come up with a model to try and show people what he thought an atom looked like. And so it was his belief that an atom was a round sphere that was essentially positive, but it was full of these little negative pieces that had kind of been shoved in there, so to speak. And he was trying to describe it to his colleagues, and he told them it looked like a plum pudding. Well, that's great if you're English and you eat English desserts. However, most of us are American, and we have probably never had a plum pudding. This is a plum pudding, and plum pudding is it's not like what we think of as pudding. It's nothing like chocolate pudding. It's really more like a cake, except for it's not baked in an oven. It's steamed in a water bath type of thing. So it has a little bit different texture, but it's more similar to cake for us than it is pudding. This is a plum pudding. It's kind of roundish, and then it has all kinds of chopped up plums in it. Maybe for Americans, if we had a chocolate chip cookie that we could make to be a round sphere instead of a disc, perhaps that would be a good description. But I've never had a cookie like that, so I guess we'll stick with the plum pudding for now. One of J.J. Thomson's co-workers, Thomson was kind of like Ernest Rutherford's boss, so to speak, was Ernest Rutherford. Rutherford learned a lot from J.J. Thomson, and he conducted some of his own experiments, and the most famous one, which is one of the most critical experiments that's been conducted regarding figuring out how atoms work, is the gold foil experiment. And this experiment helped Rutherford to discover what we now know as the nucleus. What he did was he took and he shot a high energy beam of alpha particles. Alpha particles are positively charged, and he shot them into a piece of gold foil. Gold foil is very much like aluminum foil, only made of gold instead of aluminum. So here we have kind of a sketch of what he put together. He had kind of a semicircle type of barrier there that was coated on the inside with zinc sulfide, which is kind of fluorescent. In the middle was his piece of gold foil, and then outside that semicircle protective area, he had a lead box that shot out the alpha particle stream. Again, this video will be available to you to watch, but not right now. And we're going to go past this for a moment. All right, so the conclusions that Rutherford came to, because one of the things that he observed as he shot these beams through was that most of the alpha particles went straight through the foil and bounced on the screen behind. And so because that happened, he concluded that atoms are actually made up mostly of empty space. It's a really weird thing to think about, the fact that an atom is made up mostly of empty space. Everything in the universe is made up of atoms, including yourself, and yet atoms are empty space. What does that mean about us and other things? Something to ponder. All right, another thing that he observed was that some of those alpha particles, a few of them, were deflected at small angles. When this happened, he concluded that those alpha particles that deflected at the small angles came close to something that was small and positive. He later went on to call this the nucleus of the atom, the area where the positive part of the atom is located in the middle of the atom. And then once in a while, the alpha particles would deflect at these really large, crazy angles. And because of this, he concluded that those alpha particles must have hit a very small, very dense, positively charged center. And that is what we now know of as the nucleus of the atom, the very center of the atom that is full of positive particles called protons. Well, Rutherford didn't know that nucleus was made of protons. He knew it was positive, but Eugene Goldstein, who was doing some experimenting around the same time as Rutherford, he discovered that nucleus was actually made up of little parts, and those parts are called protons. Then, a while later, a little more recently, I say that because James Chadwick here actually was alive when I was born, only for a little while longer, but he was alive when I was born, so it wasn't too long ago that he did his research. And he discovered what we call the neutron. Neutrons are neutrally charged. They are neutral. They are not positive. They are not negative. The reason they were discovered so late is because they're not positive or negative. It means they don't really react to anything. You put something positive by it, it doesn't do anything. You put something negative by it, it doesn't really do anything. And so James Chadwick was able to figure out that despite the fact that it didn't react with anything, he was able to discover the neutron. So we now know about negative electrons, positive protons and neutral neutrons. In our next lesson, we're going to take a look back at John Dalton and his 4 postulates, and we are going to see how correct he really was. And I think you're going to find that while he wasn't completely correct, it's remarkable how much he did get right. All right, thanks a lot, ladies and gents. We'll talk to you later.